Namaste. I am Kamala Soppin, Assistant Professor of Physics, DRM Science College, Davangere, Karnataka. In the previous video, Interference Part 1, we already discussed some basic concepts of interference and also the theory of interference in thin films. In this video, we are going to discuss how the interference pattern is formed in air wedge. Then, what is air wedge? A thin film of air having zero thickness at one end and progressively increasing to a particular thickness at the other end is called. Here, are formed between two glass plates. If a piece of paper or wire is kept in between the two glass plates at one end and tightened at the other end, we get air wedge. Wedges are used to push materials apart or cut things. Scissor is a good example for wedge. Now, we will discuss how the interference fringes are produced with an air wedge. Consider two plane surfaces OA and OB inclined at an angle theta enclosing a wedge-shaped air film. The thickness of the air film increases from O to A. Here, one wave is reflected from the upper surface of the air film and the other wave is reflected from the lower surface of the air film. These two reflected waves superpose give rise to interference pattern. When the air film is viewed with reflected monochromatic light, a system of bright and dark interference fringes are observed. The fringes are equidistant and parallel to the intersection of the two surfaces. Let us discuss the theory of air wedge. Suppose the nth bright fringe occurs at the point Pn. The thickness of the air film at Pn is Pn/Qn. As the angle of incidence is small, we have cos r is equal to 1. In case of reflected light, for bright fringe, the optical path difference is 2 mu t cos r minus lambda by 2 and it is equal to n lambda, or 2 mu t cos r is equal to 2n plus 1 lambda by 2. Here, for air, mu is equal to 1 and cos r is equal to 1 and t, the thickness of the film, is Pn/Qn. Therefore, substituting these in the above equation, we get 2 Pn/Qn is equal to 2n plus 1 lambda by 2. This is equation 1. The next bright fringe n plus 1 will occur at Pn plus 1 such that 2 Pn plus 1 Qn plus 1 is equal to 2 into n plus 1 plus 1 lambda by 2. This is equation 2. Then subtracting the equation 1 from equation 2, we get Pn plus 1 Qn plus 1 minus Pn Qn is equal to lambda by 2. This is equation number 3. The equation 3 tells us that the next bright fringe will occur at a point where the thickness of the air film increases by lambda by 2. Suppose the n plus mth bright fringe is at Pn plus m, then there will be m bright fringes between Pn and Pn plus m, such that Pn plus m Qn plus m minus Pn Qn, it is equal to m lambda by 2. This is equation 4. If the distance Qn plus m Qn is equal to x, then theta is equal to Pn plus m Qn plus m minus Pn Qn divided by Qn Qn plus m. is equal to m lambda by 2 divided by x. It is equal to m lambda by 2x. This is equation 5. Or x by m is equal to lambda by 2 theta, where x is the distance corresponding to m fringes. Then the fringe width beta is given by beta is equal to x by m, and it is equal to lambda by 2 theta. Suppose the thickness of the air film at Pn plus m is T and the length of the air wedge at Qn plus m from O is L, then theta is equal to T by L. Therefore, the equation 6 becomes beta is equal to lambda L by 2T, or the thickness of the air film at a distance L is given by T is equal to lambda L by 2 beta, where lambda is the wavelength of monochromatic light, L is the length of the air wedge, and beta is the fringe width. From this equation, it is possible to measure the thickness of the paper or wire. This is one of the applications of interference. The following picture shows that interference pattern produced by an air wedge. Thank you.